My name is Olivia Sue, and I will be presenting on compilation of sparse array programming models. This work was done in collaboration between MIT and Stanford University. Python is an extremely popular language with a large ecosystem, which includes the NumPy array programming library as well as the SciPy array programming library. Both NumPy and SciPy are extremely useful for high-level applications, including digital signal processing, data analytics, scientific computing, machine learning, and more. Currently, the estimated user base for NumPy and SciPy range from 6 to 25 million users. However, NumPy and dense array programming is not enough because NumPy cannot support sparse objects and applications that a programmer or user would want to represent. For example, this includes sparse tensors and arrays, graphs, and database relations. Dense computation on these sparse objects is either too expensive or the objects are too large to fit in memory. However, all of these sparse objects are representable with compressed arrays. If NumPy or dense array programming is not enough, let's consider prior work done on sparse tensor algebra through the Taco compiler. Unlike dense array programming or NumPy, sparse tensor algebra only supports computation over the plus multiply semiring, meaning it can only reduce across addition and support multiplication and addition operators, as shown through this index notation expression. Like dense array programming, sparse tensor algebra supports multidimensional tensors and arrays, with sparse linear algebra only supporting vectors and matrices. Unlike dense array programming, which only supports a dense data representation, sparse tensor algebra can store data in both dense and sparse representations. Even with the consideration of the sparse tensor algebra, our previous work on sparse tensor algebra is still not enough, because sparse tensor algebra cannot perform nonlinear calculations like dense array programming can. As an example, sparse tensor algebra cannot support Boolean functions that are useful in digital image processing like medical imaging, where the images are represented by matrices or tensors, and the Boolean functions are required for image post-processing. Sparse tensor algebra cannot support computation across arbitrary semirings. For example, graph algorithms, graphs are represented as adjacency matrices, require support for arbitrary semirings beyond just the plus multiply semiring. One example graph algorithm that uses a different semiring includes the single source shortest path algorithm, which requires the min plus semiring. To address the lack of sparsity support in dense array programming and the lack of arbitrary function support in sparse tensor algebra, we propose sparse array programming. Starting with the sparse tensor algebra programming paradigm previously shown, we now add dense tensor algebra and dense array programming paradigms into our table, with both of these programming paradigms not supporting a sparse data representation. However, both of these programming paradigms support array slicing, where, for example, in NumPy, you can window into an array with a start, stop, and step. Additionally, dense array programming supports any arbitrary function and any arbitrary semiring. An example of this is shown above with the XOR function. And now we introduce sparse linear algebra on any semiring. An example of this is seen through the GraphBLAS graph algorithms library. And this programming paradigm supports any arbitrary semiring as well as sparse data representations. However, all of these sparse programming paradigms that support sparse data representations only support compression of a zero fill value, and one can imagine that a user would want to compress data along any arbitrary fill value. And this is why we propose sparse array programming, which supports a superset of all of these features. We show that sparse array programming is a superset of all of the previously mentioned programming paradigms. We also demonstrate that sparse array programming can be performant. We can generate code that NumPy and dense array programming originally couldn't. Additionally, we produce the same code as the existing state-of-the-art Taco for sparse tensor algebra expression. And furthermore, we are competitive with hand-optimized libraries like Sweet Sparse GraphBLAS. And finally, we demonstrate how to generate more performant code for sparse array programs than the current state-of-the-art, namely PyData Sparse. Here's an overview of our compiler for sparse array programs. We build our system atop the Taco Sparse Tensor Algebra library, and our compiler takes as input an array index notation, which is the algorithm that has been extended to support user-defined functions and array slicing. Our compiler also takes in a format language that describes the array compression format with now any arbitrary fill value. And finally, our compiler takes in a scheduling language that describes the optimizations and transformations of our sparse array program. The rest of the talk, I will go on to talk about our extensions to the Taco library that allow us to produce functional code from our sparse array program to imperative C-like code using concepts like sparse iteration spaces and an intermediate representation we call iteration lattices. All of the gray boxes denote new contributions of our work. Now we will demonstrate the input API and output code of our compiler using the greatest common divisor example. Here is the input API for our compiler, and I would like to note that we now support explicit fill values within the format language. Additionally, the array index notation now takes in arbitrary function calls like GCD. Here's a user-provided definition of the GCD function, and both of those get combined into a C-like imperative code. The problem with this code is that it's very complicated, and a user wouldn't want to maintain this by hand. Additionally, what if your input function changes from GCD to something else? Then the output code would completely change as well. We are again displaying the GCD user-defined function from the previous example, where the user has to provide two descriptions of the function. The first is the computation that needs to occur for the GCD function, as well as the iteration space of the function. And the iteration space tells the compiler what computation needs to be explicitly calculated, as well as what computation can be skipped due to the compressed data structure representation. Additionally, functions in our compiler can be described in a second way, where functions provided by the user can actually be defined using properties, and our compiler can automatically infer the iteration space from the provided properties. So what exactly is an iteration space? Let's consider a 3x4 dense matrix, and this matrix can be represented as a uniform grid of points. We call this the dense iteration space. Now let's consider a 3x4 matrix that is sparse. Every explicitly defined value within this matrix is still a point in this grid. However, all of the inferred fill values are removed from this grid. We call this the sparse iteration space. Additionally, a sparse iteration space can be thought of as a set because every point that is explicitly defined lies within the set of this matrix, and every point that is an inferred fill value lies outside of the set. This leads us to prior work on sparse tensor algebra, which allows for multiplication and addition. Multiplication can be considered an intersection of two sets, and addition can now be considered the union of two sets. On the previous slide, I defined what an iteration space is. Our compiler, unlike prior work on sparse tensor algebra, will explicitly lift the iteration space from our operators, generating a set algebra, which can be thought of as a Venn diagram. With the explicit iteration algebra, we will now demonstrate how our compiler generates code. First, our compiler takes the iteration algebra and decomposes any union within the algebra into unions of disjoint intersections. Each disjoint intersection region within the set expression is then mapped to a node of an intermediate representation that we call an iteration lattice. Here is the first disjoint intersection subset. Then, from the iteration lattice, our compiler is able to generate the correct while loops and if conditions to produce correct code. Here, we demonstrate the next disjoint intersection subset and the correct code that's generated from our compiler. And finally, the last disjoint intersection subset, which completes our code generation. This slide now summarizes the full representation and code for vector-vector addition. However, in order to represent any arbitrary function, we can't just have unions and intersections as in the prior work on sparse tensor algebra. Therefore, we introduced the notion of a set complement, where subregions within our set algebra can omit computation. The way we generalize to set complements for any region, we now create an omitter point within our iteration lattice where computation is omitted. This is useful, for example, in the XOR function where computation should not occur when both the B and C vector have values. With the addition of a set complement, we are now able to describe any sparse iteration space beyond intersection and union. Here are the binary iteration spaces that we can now describe, but our compiler also extends beyond two input operands. Now that we've motivated a need for sparse array programming and described how our compiler works, we answer the question, will our compiler perform well? We do this by evaluating our compiler in three areas. First, sparse array programming has a long tail of arbitrary functions, and we compare our compiler against the current state-of-the-art baseline for a few of these functions. Additionally, we compare against the baseline for fused calls as well. Next, we compare against handwritten, hand-optimized code for graph linear algebra kernels. And finally, we evaluate our system in end-to-end applications like image processing. For the first evaluation, we compare against PyData sparse on built-in NumPy library functions called universal functions. Here, I show the speedup of our system over PyData sparse for 4 separate ufuncs on 6 different Sparse tensor datasets. We demonstrate a speedup over PyData sparse of between 3 times to about 20 times because we generate bespoke code from our compiler, whereas PyData sparse needs to transform the sparse data representation into dense temporaries first before calling a dense function from NumPy. We also evaluate our compiler for fused NumPy universal function calls, and we demonstrate a speedup over PyData sparse of between over 10x to over 50x on the Frost dataset, since our compiler is able to generate bespoke code for the complicated 3 input operand iteration space, whereas PyData sparse now needs to generate even more dense temporaries for the nested function calls, as well as compute intermediate values from the first function call that can later potentially be thrown out. Next, we evaluate our compiler on graph linear algebra kernels against the hand-optimized sweet sparse graph BLAS library. We compare against this library for 2 types of data. We show the absolute runtime of our system versus their system in parentheses. From the geometric mean speedup of the table, you can see that our compiler is competitive, if not better, which motivates the use of our compiler since our compiler also supports more general types of computation. Finally, we evaluate our compiler on end-to-end applications. One example is this medical imaging edge detection where the expression is shown in the middle. Our results demonstrate that our compiler outperforms both PyData sparse and NumPy. We're able to use NumPy as a baseline in this end-to-end application because the images are small enough to fit within memory for dense computation. Additionally, notice the x-axis on the performance graph. The x-axis is the number of dense or total elements within the image. NumPy's computation is proportional to the number of total elements within an array, whereas PyData sparse and our work are both proportional to the number of non-zeros within the array. In conclusion, a user can now write any function across any sparse array through the Sparse Array Programming model, and we demonstrate that with compilation, we're able to achieve good performance. We are working with the SciPy and Julia teams to integrate our compiler into their backend, and this addresses the SciPy future roadmap goal where they would like to implement sparse arrays in addition to sparse matrices.